Hello everyone, welcome to the lecture 35 in the course Diffusion in Solids. So this is the last lecture of the week 7 and therefore as always it's a tutorial lecture, and I would suggest like I have done previously that please try to solve the problem on your own before you proceed to see the answer. So here we cover some basic problems on the content that we covered in this week. So question number 1, CALPHAD principle involves generating thermodynamic descriptions for various phases based on. So here are the options: the internal energy, enthalpy, Gibbs free energy, or Helmholtz free energy. So here the correct option is option C, which is the Gibbs free energy. This is not very difficult to understand because the equilibrium itself demands that the Gibbs free energy of the most stable phase should be the lowest, and these are the thermodynamic principles which are basically utilized by CALPHAD approach to do the phase predictions and other calculations. Question number 2. Refer to the below expression for excess Gibbs energy of a solution. G excess is equal to summation xi xj lij. Which of the following solution model does the above expression correspond to? So the options you will see: the subregular solution model, regular solution model, Redlich-Kistler polynomial, or the compound energy formalism. So these are the excess Gibbs energy models which we have seen. So in the regular solution model, the excess free energy, remember the free energy has two contribution. One is the ideal contribution, and then you have the pure one, and then you have the excess free energy. So this excess free energy is what is modeled using different types of solution models. So the regular solution model says that the G excess can be written as summation xi xj lij, where lij is the interaction parameter between components I and j, and it assumes a symmetric mixing behavior. Then the subregular solution model, it considers the variation of this interaction parameters on the composition. So here it is written as xi xj lij 0 plus lij 1 multiplied by xi minus xj. Then one of the model which is widely used for the asymmetric mixing is the Redlich-Kistler polynomial, which is summation of xi xj summation lij xi minus xj to the power k. Then if there are ordered phases, the compound energy formalism is what is used, which describes the ordered phases with multiple sublattices, and each sublattice can accommodate specific elements or species. So in the question we were given the excess free Gibbs free energy is modeled with this function, which corresponds to a regular solution model. Now question number 3. Experimental data is critical to perform phase predictions using CALPHAD approach. Which of the following performs key part of this data set? So for option 1 is phase equilibrium data, second is mechanical properties, third is electrical properties, fourth is activity and partial molar volumes. So since we are talking about the phase predictions using the CALPHAD approach, what we are looking at is the data related to the equilibrium of the phases, either the variables or the parameters which can affect. So in this case, the correct options come out to be phase equilibrium and the activity and the partial molar volumes. So sorry, this is the option is wrongly written here. Let me correct. So this should be A comma. Moving ahead, which of the following form key limitations of the CALPHAD approach? So here are the options. First is dependence on quality of experimental data. Yes, it is true, it is a limitation of the CALPHAD approach, because if the data is not accurate or it is not reliable, then the predictions will also be erroneous or not robust enough. Second is calibration and maintenance of databases. This is again true, because as the new new types of phases or new research is going on, so the databases have to be continuously updated. So that is required. So that is intensive task. So hence it requires a lot of efforts. Third is lack of adaptability to new methods. This is not a limitation. In fact, CALPHAD approach basically is very adaptive to new methods. Inability to integrate kinetic data. This is we have seen in the previous video also, that and others as well, that we can very well perform the diffusion simulations, the kinetic simulations. So all you need is a right kind of a mobility database. So it is not a limitation of CALPHAD approach. So the correct options are A and B. Moving ahead, question number 5, the CALPHAD implementation software which is open source is Thermocalc, FactSage, Pandat, JMet Pro, or none of the above. So this, if we have seen this before, that all of these are not open source. They do have a free license, but they also have a commercial license as well. So this is not completely open source. So the correct option is none of the above. The open source actually is the Open CALPHAD. Moving ahead, question number 6, which of the following databases is used by diffusion module DICTRA of the Thermocalc? Gibbs Energy database, mobility database, activity database, or enthalpy database. So in this case, in the diffusion module, because the purpose is to perform kinetic simulations. Okay, so just in the last video we had seen the examples of carburization, or we had seen the example of moving boundary problem. So that all requires the knowledge of how fast the diffusion happens, because we saw that, for example, moving boundary is controlled by the diffusion of atoms across it. So therefore, what we require is a database which has the kinetic parameters in it, so to say is the mobility database. So the mobility of different atoms in various phases. So the correct option in this case is option B. Question number 7, select the applications for which the DICTRA module is used. So microsegregation during solidification, coarsening of precipitate phases, generating phase diagrams, or growth of the secondary phases. So the DICTRA module, which is the diffusion module, it performs or it is used for the applications where a moving or a kinetic process is involved. So you can see that except for the option C, all are correct here. So answers are A, B, and D, because each of these A, B, and D basically involve the diffusion control phenomenon. Then question number 8, select the correct statement or statements about a database used in the CALPHAD implementation software. So the first statement, it is an organized collection of data that allows for efficient access, management, and updating. Yes, it is correct. This is indeed the definition of database. Second is it stores critical information derived from experiments and simulations. This is also correct. The database has the data which is not only derived from the experiment, but also derived from the simulations or the first principle calculations, ab initio methods, and so on. The quality of database depends on the accuracy of the experimental data. This is true that how accurate are the experimental data will also determine the quality of the database, because experimental data are input to the database. So the better the data are, the better is the quality of the database. The fourth, the quality of database is independent of optimization techniques. This is wrong. It does depend upon the optimization techniques, what optimization techniques are utilized, so that it will influence the quality of the database. So, the correct options are A, B and C. Question number 9, identify the correct sequence of steps in CALPHAD methodology for creating database. So, these are the options: data capture, then storage and validation, assessment and optimization. This is not correct. The first is data capture, that is correct. But after that, what is done is first the assessment. Here you can see the assessment, then optimization, and finally it is the storage and the validation. So, in this case, the correct option is option D. Now, question number 10. Suppose a student wants to generate phase diagram of multi-component cobalt, chromium, iron, nickel system. How many assessed binary systems should the selected database contain ideally for making reliable predictions? See, here it is a 4 component system. So, ideally what we need is basically all the binary, all the possible binaries, if the information is available, that is the ideal case. Of course, in addition you also need ternary interactions if ideally possible, unary interactions are also should be present. But as far as the binary is concerned, then all the binary systems, if they are assessed, thermodynamic assessment is done, then it is very likely to give a good prediction. So, now it is a question of how many binaries systems are there in a 4 component system. So, simple combination permutation will tell you that it is 4C2, which is equal to 6. So, the correct option is C here. Going along, for optimization, modules used by Thermocalc and Pandet are dash and dash. So, these are the different CALPHAD implementation softwares. They use different optimization modules. For the Thermocalc, it is known as a Parrot module, and for the Pandet, it is known as the Pan optimizer. Question number 12. The optimized thermodynamic parameters in the database are stored in a file which has the following extension. So, this is that after all the steps like I mentioned previously are done, then the entire thing is stored in a database file which has a standard universal extension. So, which of them correctly represents that? .tdf, .tdb, .thb and .thd. So, here the correct option is the .tdb, it is the thermodynamic database file. Question 13. A thermodynamic database containing nickel as one of the constituent will contain free energy description of pure nickel in which of the following solid crystalline phases? FCC, BCC, HCP or all of the above. Let me repeat the question again. Suppose if there is a thermodynamic database which contains nickel as one of the constituent, this will contain free energy description of pure nickel, of course, but in which of the following solid crystalline phases? Whether it will be FCC, BCC, HCP or all of the above. Now, here please do not be confused by the fact that nickel is FCC, so only the free energy description of FCC should be available. See, when we are talking about the nickel being FCC or for that matter any particular phase being an equilibrium phase, how do we know that that is an equilibrium phase? How do we know that FCC is the most stable phase for nickel? It is by comparing the free energies in different crystalline phases also. So, therefore, the description of nickel definitely contains BCC and HCP. As well. This is one reason. Second, also this is little bit going into the thermodynamics part, but if you remember our discussions where we revised about the solution models, where you write the free energy of different phases. So, suppose if you want to write a free energy expression for solutions where chromium is, let's say, 90-95%, and nickel is dissolved in it 5 to 10 atomic percent. Now, here the overall solution structure is a BCC structure. Okay. So, now what you need when you write the free energy description or the free energy expression for this alloy is, if you remember, the expression is of the type XAGA plus XBGB. So, you need for this the free energy of nickel in BCC form. However high or low it is, you need the expression, you need the quantity which is free energy of nickel in BCC form in order to predict or in order to write the free energy expression of the BCC phase where nickel is added as a minority element. So, therefore, just because nickel is FCC, it is not sufficient, or it is not really true that it will only have the free energy description of pure nickel in just FCC phase. It does have in FCC, BCC and HCP as well. So, the correct option here is all of the above. The question number 14, the current phase diagram of cobalt tin contains which of the following phases that was not present in the older phase diagrams. So, the options are alpha CO3 SN2, COSN, alpha COSN3 or beta CO3 SN2. So, this we said when we were talking about the continuous evaluation of the databases, the need to update them. So, this here the correct answer is alpha COSN3, which was found in the research experiments later on. People found, so then it was updated, and now the phase diagram contains the COSN3 phase as well. Question number 15. So, a phase diagram does not contain the lines for magnetic transitions. However, the information regarding magnetic behavior is included in the database of several elements. So, can we explain this? See, the question is, for example, if you look at an iron carbon phase diagram, you will see a transition from BCC iron to FCC iron, then again to BCC. But you will not see there a transition from paramagnetic to a ferromagnetic phase. Okay, so those equilibrium are not depicted in the phase diagram. But we know from the considerations of entropy and free energy that free energy has the magnetic contributions toward it. So, why the thing is there any contradiction here? The answer is actually there is no contradiction. The concept of the phase diagram itself, it involves predicting the equilibrium as a function of temperature and composition, and the very definition of the phase itself, if you see, it is a physically homogeneous, chemically homogeneous and mechanically separable. It does not include the behavior about the magnetism, so to say. So, if you see a paramagnetic and a ferromagnetic BCC iron, it will have a similar crystal structure, same compositions, and therefore, it is not considered as a separate phase in the phase diagram nomenclature. So, therefore, it is not reflected in the phase diagram. In addition, another fact also that is there, these transitions are not the first order transitions. However, this is also true that the free energy of each phase is also influenced by the magnetic ordering or the magnetic domains that are present in the material. So, which can lead to in fact the changes in the Gibbs free energy. In fact, if you think about it, just for some thought, you see that in many of the examples we saw, for example, we saw titanium, hafnium, zirconium, you see tin, and many other examples you will see that the closed packed structures are the one which are stable at a lower temperature, and the open structures like BCC is stable at a higher temperature. But in the case of iron, you have a BCC structure which is stable at the lower temperatures as well. And why is it happening? So, there the influence of the magnetic behavior is the magnetic contribution to the Gibbs free energy comes into picture. Moving ahead, Question number 16 is moving phase boundary is a boundary or interface between two phases in a system that changes position over time due to diffusion driven mass transport. This is true or false? This is true. This is how the moving phase boundary is defined. Basically, we saw, for example, in the case of interdiffusion, this boundary interfaces as the new phases develop. So, the interface keeps changing its position as a function of time. Question number 17. In diffusion simulations, we do not set the material composition because of the non-steady state behavior. Is it true or false? This is true. We saw in the previous video that for example, if you want to simulate moving phase problem, carburization problems. So, in that scenario, the composition varies as a function of distance, as a function of time, and that is why we do not set any composition. Rather, we tend to define a certain maximum or range in which the composition varies, but we do not select a particular composition. So, this is true. Then question number 18, a homogenization function is a method used to deconvolute the diffusivities of individual phases in a multiphase region. Is it true or false? This is false. It is actually the reverse. We use the homogenization function in a multiphase diffusion problem, but it is not to deconvolute the diffusivities. It is actually to combine the diffusivities of individual phases, so that a single effective diffusivity can be used to perform the necessary kinetic simulations. So, this is false. So, with this we will end this tutorial lecture, and we will continue with the next week. Thank you.